demo we're going to be using is one of our workshop studio demos. And as we said, it's going to be RAG with Bedrock knowledge bases and Postgres Aurora. And I'll share the link at the end of the demo as well, so you can take a little look at it and give you all the steps you need to get you going and try RAG out for yourself. So how are embeddings used? So we talked about the embeddings earlier. So if you take our blue vase, on our product catalog, so essentially, in this case, it's going to be a PDF document. In our demo, we'll be looking at Postgres 16 documentation. You grab that document, and what you're going to do is you break that document down into chunks, and the workflow will do this for you. The chunks are then passed into an embeddings model, in our case, Titan embeddings. And what you'll get is you'll get the embedding, which is a vector, a very large number. You'll get metadata, where the documents come from. You'll get the chunk of data, and you'll also get a ID column for the column, which we'll see in the demo. And this is all passed into an Amazon's Aurora data store. You can use whatever data store you like. When you're choosing your data store, it really is what is your familiarization with those different types of data stores. And this is the idea of having the different options for you. So if you've got a user, let's go back to the demo before. What does a blue elephant vase cost? That was the question. That's passed into the Titan embedding model. So one thing to point out here, this was a slide what was missing earlier, is the embedding model you're using, you need to use the same embedding model for the embeddings you're storing, as well as the question you're asking. And then, so back to that question we asked, the blue elephant vase, what's it cost? This is where the magic happens a little bit. You're doing the similarity search against your vector type, and then you're passing the question and context back to a large language model. In our case, we're using Claude 3 Haiku, and then you get a response back to the user, a human type-like response, as well as you'll get the metadata type, and you'll get where the data come from as well. So, and if there's multiple chunks of data, you can see the multiple chunks of data it's come from. So let's have a look at I'm sorry, I'm not used to using a mic, so I'm sorry if the sound keeps going in and out. So, so this is the workshop studio. It's I don't know if you can all see it. Yep. So we got a Postgres database pre-created. It's Postgres Aurora database. And I'll kick it off now. And we're going to be using Bedrock. We're going to be using Cloud9 as an IDE, but that's just really to make the simplicity of this demo. We're using 15.6 is the version of Aurora. First thing we're going to do is enable the data API. This takes a couple of minutes to do. While that's enabling, what we're going to do is we're going to flip over to Cloud9, and this is where we're going to connect into our database. Like I say, we're using Cloud9. We just want a PSQL command. If you were testing it yourself, you can connect however you like. So once we've got PSQL and we've connected into the database, what we're going to do is we're going to enable the vector type, and we're going to actually create a table and an index where we're going to store our vectors. So you see, we'll create the extension now, we'll create the table, and we'll create the index. And the index is on the embedded, so the vector type, so we can do our similarity search. So now they're created, what we're going to do is we're going to go into Bedrock, and what we're going to do is enable our model access. What you'll be able to initially see is that we've already pre-enabled some model access. So if you go into the model access area, you can see some of our models are already access granted. If first time using this, they would all be available to request. What you can do is edit the model access, enable the models you want access to, click next and click to accept. You can then start using those models inside of Bedrock. So now we've got those models enabled. What we'll check is our Aurora database. We can see that our data API is enabled now. So now our data API is enabled. So Bedrock has access to our Postgres database. At this point, it's connectivity. So what we're going to do is we're going to go back to Bedrock, and we're going to go to knowledge bases in the builder tools, and we're going to create a knowledge base. So if we click on create knowledge base, first thing we'll do, give the knowledge base a name, simple name here, PG test. We're going to create a new service role. You can use existing service roles if you want. It's not uncommon for people to create their own separate pipelines for service roles. We'll then connect to a data source. In this case, we're going to use an S3 bucket. The S3 bucket is pre-created. And this is where we're going to store our data, essentially our PDFs in this case. And we have a PostgreSQL PDF. So we select that S3 bucket, click Next. Then we're going to choose our embedding model. So we're going to use Titan embeddings, G1 text. We'll then move on to our vector store we're going to use. We're going to be using Amazon's Aurora. So we'll click into Aurora. And then we just need to give credentials for our database. So first thing we're going to do is give the ARN for our Aurora cluster. So we'll select that, put that into the knowledge base. Then we need to look at what is our database name, so the database we connected to earlier. Also the table name we created earlier. And next thing is our secrets. How do we connect to the database? We're using Secrets Manager. So you will give the ARN for the Secrets Manager to the knowledge base. And you're at the point now where you're going to start doing your table definition. So we create the table. So the index field mapping we did before was embeddings. That was the index we created on that field. The text field name was chunks. This is where we're going to store the chunks of data. The metadata field was metadata. And the primary key was ID. So we'll quickly just go back to Cloud9 so you can see those two match up. The key point here is you can kind of call the table what you like. You can call the columns what you like, the index what you like. The key point is mapping it back to Bedrock and making sure when you're creating your knowledge base, those two map up. If you don't, you will get some errors, as I've certainly found when I've done it in the past. So yeah, do make sure you get it right. So click Next and move on to creating your knowledge base. So fairly simple process to create the knowledge base. This takes a couple of minutes if you're using a pre-created database. If you're using a starter database like the OpenSearch cluster serverless, it will take a little bit longer. So we have the knowledge base created now. You can see our PostgreSQL document in the S3 bucket. This is what we're going to essentially break down our document into chunks and get some vectors from so we can do some searching. So first thing you need to do is you need to, once the knowledge base is created, you need to sync up your data source. The process of syncing your data source is, this is where it will do all the magic. It will go in, break your document down into chunks, store the vector, pass this into your Aurora Postgres database in our case. The process, as you can see, is very quick for one document, one small document. More documents you have, the longer the process will take. So once you're at this point, what you can do is actually test your knowledge base, start trying it out. So this is where we're going to choose our large language model we want to query against it. So we're going to use our Claude 3 Haiku, which we'll be passing our output into. And we're going to ask a question. So we're just going to ask a simple, describe how PGStat views tracks. And you can see we get a response back from our knowledge base. We get the source of the knowledge base, where did it come from. We also get the more details, which is the chunk of data it's done the similarity search against. So you can see that's the chunk of data it's kind of give you the human response back from. And what we'll actually see now is we'll take a look at how that looks in the database. This for me was certainly, as I'm a database guy in the past, this is where I like to see how things work. You can see how that document was broke down. So we have a PDF document. It was broke down into 119 chunks. And for each of those rows, what we'll see now, we're just doing a little query against the database here, limit with one row, so we just show one row back. You start to see what is the representation, what does it look like. So we have metadata, so the data, where's it come from? We actually have the chunk of data. We have the vector, the large mathematical number where kind of, again, some of the magic happens. And then we have the ID field for the column itself. Like I say, for me, this kind of brought it to life a little bit when I was first looking at, when we were using vector and knowledge bases and trying to understand how does it actually start querying against this document, and you can start to see how you use some of the embedding models to be able to bring this information to life. So this is available on our demo at one of our workshop studios. If you want to take a quick look at that, it will also be available at the end after this as well, where you've got the link for it. I am interested, is anybody using any form of RAG at the moment? Yeah, cool. Oh, so there's a few people. Anyone using it in prod? No. Okay. That's cool, though. It'd be interesting to hear some of your use cases. So, I mean, we've done this talk a few times, and it usually is a few people, in the audience who are using it, and it's quite interesting when you start to talk to them about what you're doing and how you're using it, because this is where it comes to life a little bit, the use cases. So why would you use Postgres as a vector store? So we touched on it a little bit before. Probably you're already using the data, you're using Postgres. You think, well, okay, I'll not go and learn another data store. I'll use Postgres. It's a good way to go. Postgres is open source. It's not owned by one company. It is truly open source, multiple contributors, enterprise scale with the features, what's in Postgres. I mean, I'm an Oracle guy, come from Oracle, not Oracle, but worked with Oracle in the past a lot. Started using Postgres about 7 years ago. Truly impressed by the capability of Postgres and what you can do with Postgres. But one of the biggest bits is it's extensible. You can have extensions. So instead of having to wait for core code to go into the Postgres versions, you have these things called extensions, and that's what PG Vector is. PG Vector, there's actually active contributing to that actual extension itself. We have contributors at AWS as well. Giorgio will touch on some of those names as he goes through his section. But that for me is why you'd really look to use it. Just out of interest, any of the guys who put the hand up, anyone using PG Vector? Yeah, cool. Oh, one, excellent. So come and have a chat later at the end. Yeah, be interested to see what you're doing with it. So that's great. So I'm going to pass you to Giorgio now, who's going to dive deeper into actual PG Vector itself.
Thank you, Tony. So, Giorgio. And PG Vector is an open source extension that added to a vanilla PostgreSQL database the vector data store and the vector search capabilities. It had the vector data type. As you know, probably a vector is a numerical array defined on n dimension, normally hundreds of dimensions. Each dimension is a float data type that consumes 4 bytes. And together with the data type, it also had 2 kinds of indexes, the IWF flat and the HNSW, that we will see much more detail. And leveraging on these indexes, it's possible to execute an approximate nearest neighbor search, alongside with an exact nearest neighbor search that is still available. And if you have already your transactional data inside the Postgres database, you can collocate your transactional data together with generative AI data. And this is much more efficient because you don't need to synchronize data between different systems. And finally, you can choose between different distance operators. The most common, the most used are the first 2. The first one is the Euclidean distance, the linear distance between vectors. And the second one is the cosine distance, that is the angular distance between vectors. Okay, but before going ahead with a deep dive on the different index type, let's see an important concept, that is the concept of recall. Because the recall, when you execute a similarity search, is the effectiveness, the measurement of the effectiveness of your result. So if you want a recall of 100%, it means that you want to retrieve for sure the closest result to your query vector. And to do that, you need to execute an exact nearest neighbor search. So you need to compare your query vector with all the vectors inside your table, inside your data store, dimension by dimension. And you can imagine that this kind of operation, when you have millions of vectors composed by hundreds of thousands of dimensions, is a huge operation in terms of resource usage, but also elapsed time to execute the query. So has been introduced the vector indexes that allow you to execute an approximate nearest neighbor search. This kind of research narrow down, reduce the scope of the vectors that are compared. So for sure, the efficiency is higher. You consume less resources. the latency, the response time is much more quicker. But on the other hand, you will obtain a lower recall. The accuracy of your result will be lower. So it's a trade-off between performance, resource usage, and accuracy, so recall. And all these dimensions are in tension between them. And you have to find the right trade-off for your specific use case. So now that we have understood this concept related to the recall, let's see how the vector index works in terms of vector organization, how they store the vectors, and how they execute the approximate near neighbor search. The first index is the HNSW, that stands for Hierarchical Navigable Small Word Index. It's not easy to say, to remember. And in this case, it's a graph-based index. It's a graph-based index built on multiple layers. And when you execute a similarity search, the graph is traversed, starting from the higher level, the higher layer, and moving transit to the bottom layer. And the density of the vectors increase from the top to the bottom. And at the end is returned the closest vector, the closest result. This kind of index is iterative. It means that you can build this index on an empty table, and the index is automatically updated, is automatically built. And the insert time of your vector, the time to insert your new vectors, is proportional to the size of the index. But let's see how it works with a cool animation. So when you build the index, as you can see, a graph is built. And this graph is a multi-layer graph. The density of the indexes, the vectors increases from the top to the bottom. And when you execute a similarity search, your query vector is compared starting from an entry point with the vectors to search the closest path. And in this case, the vectors are the nodes of the graph, and the link between the nodes represent the distance between vectors. So you traverse the graph, you transit to the next layer, till to the bottom layer to find the closest result. It's similar to Google Map research. You start from the country, you move to the region, then to the city to retrieve your final address. It's a similar mechanism, a sort of zoom in. Okay, in this case, you can tune this kind of index through some parameters that have also an influence on the final accuracy, on the recall. You have two parameters during the index creation that are M and EF construction. M represents the maximum number of connections for each vector at each layer. Instead, the EF underscore construction represents the number of vector candidates that will be evaluated during the index creation. Instead, before executing a similarity search, you can specify this parameter, EF underscore search, that represents the number of vector candidates that will be evaluated during the research. But let's see an example. In this case, we are creating a table. As you can see, there is a column defined as a vector data type, 1,536 dimension. That is exactly the number of dimensions that are returned by the Titan embeddings model, the model that has been used in the demo presented by Tony. And on top of this column, we can create a vector index. In this case, we are creating an HNSW index. We are specifying the operator, in this case, the cosine operator, so the angular distance. It will be used this algorithm to build the index. And we are specifying, yes, here's a problem. We switch the computer, the laptop. M equal to 16 and EF underscore construction equal to 64. So the two parameters that influence the index creation. And before executing the similarity search, we can specify also the third parameter, ef_search, equal to 40. These are the default value for this kind of index. And at the end, we can execute our query. As you can see, it's a similarity search query because we are executing the query using the cousin operator. Cousin operator because it must match the definition of the index. So it's an approximate nearest neighbor search. And we are specifying order by limit 5 in order to retrieve the 5 vector closest to my input vector, my query vector $1. So increasing all these parameters, you can improve your recall value to improve your accuracy. But on the other hand, as we have explained, you also need more resources and more time to retrieve your result. So it's a trade-off, as we have explained. Okay, let's see the second kind of index, IWF flat, inverted flat file index. In this case, is a key-means index. Key-means is an algorithm that partition and group your bunch of vectors into clusters. These clusters are called list. And for each list or cluster is computed a centroid. And when you execute a similarity search, you will compare your query vector only with the vectors inside the cluster with the closest centroid. So you are reducing a lot the scope of your vector data space. And in this case, the index is not iterative. You need already a table populated with vectors because the algorithm needs to compute the centroid. And without vector, it's not possible to do that. And the insert time is proportional not to the size of the vector, sorry, to the size of the index, but to the number of clusters or lists. So if you have an higher number of clusters, also the insert time is higher. Also in this case, we have an animation to better understand how it works. We have our bunch of vectors inside our table. When you create the index, as you can see, these vectors are partitioned and grouped into clusters. We have 1, 2, 3, 4, 5 clusters or lists, and for each one is computed a centroid. When you execute a similarity search, your query vector is compared with all the centroid, and then only the vectors inside the cluster with the closest centroid are evaluated to retrieve the closest result. In this case, we have 2 parameters to influence the recall. The first one that is used during the creation time is the number of lists, the number of clusters. In the previous example, we had 5 clusters. And the second one is the number of probes that are the cluster that are evaluated to find the closest result. In the previous example, we evaluated only 1 cluster, the cluster with the closest centroid. Same example of before, we create the table with the vector data type column, and in this case, we are creating an IWF flat index. The same, we use the cousin operator, and we are specifying 500 lists, 500 clusters. And when we execute, before executing the similarity search, we can say, look only at the 20, inside the 20 clusters with the nearest centroid to my query vector. And in this case, the similarity search query construct is the same than before. We are using the cousin operator, and we are looking for the 5 closest vector compared to our query vector. Any questions so far? Good. Please. This is a super interesting question, thank you, because this is one of the main differences between the HN index and the IWF flat index, because HN index is dynamic, is automatically updated. In this case, the new vector is inserted, but the centroid is not updated. So if you execute a lot of DML, so you update or delete or insert a lot of new vectors, at the end, you will have to rebuild the flat index. Because otherwise, the risk is that the accuracy, the recall will decrease. Okay. You can do that also online without downtime, but it requires a management activity. So yes, you need to manage this kind of index. Additional cost in terms of resource usage, yes. Yes, it depends because there are IOPS operations. So if you are using, for example, on Aurora optimized IO, all the costs of IOPS are included. If you don't use optimized IO, you pay for IOs, yes. Okay, but we have seen the details of these two kinds of index. Which one you should choose? So if you want a recall of 100%, you don't need an index. You need to execute an exact nearest neighbor search. So no index at all. If you have a fast indexing method, flat is a good choice because it consumes less resource, less time during index creation, but you have to manage it. So if you want instead an easy to manage index and that also provide a good ratio between performance and recall, also with the default value, HNSW is a good starting point. And for this reason, a lot of generative AI application developer prefers this index type at the beginning because it's much more simple to use, and also it's a good ratio between performance and recall. Okay, cool. We have seen some details about the mechanism to execute a similarity search, but let's see now how Amazon Aurora can boost your similarity search use cases. As you know, probably Amazon Aurora is the cloud-native relational database service with PostgreSQL and MySQL compatibility that provides the availability, scalability, and agility of the enterprise-grade databases. And now we will see how some native feature or option of Aurora can improve the similarity search. And I want to start from the optimized read with IO optimized. When you enable the optimized read option, you can do that on some specific instance classes that provides the direct attached local volume, the NVMe volume. You can enable two features, or actually two features are enabled. The first one is an additional tiering of caching. So you will be able to keep much more data near your instance database without the need to read it from the Aurora cluster storage. And the second feature is the capability to spin the biggest query, the query that don't fit in memory, for example, in the work area size, because our query that execute a complex group by, join, or sort operation. Normally, this query spills to the disk, to the EBS block volume. In this case, instead, we'll spill inside the direct attached local volume that provides a higher throughput and very low latency because it's direct attached to the database instance, EC2. And so using this enabling this option, you can improve a lot the response time of your vector search query. The second feature, we have already seen the integration of Aurora with Amazon Bedrock knowledge base. In the demo, we have used it as a vector data store. Another integration with Bedrock is the capability to access directly from your SQL code the foundation model through Amazon Bedrock. And to do that, you have the AWS machine learning extension. Then Amazon Aurora support the PG vector extension 0.7.0 that include the support for the two index type that we have described, but also some additional new features. For example, the scalar and binary quantization. Now we have no time to explore it, but we will provide you some link later after. And finally, Aurora has the capability to scale up and scale out, also for handling the most demanding vectorial search workloads. And now a couple of benchmarks to see how this feature can boost your similarity search use cases. Here we are comparing two Aurora clusters with the same instance class in terms of CPU and memory. But as you can see, the yellow one has the D suffix. D means that has a direct attach local volume, this instance class. So we can enable the optimized read features. We are using a benchmark, big ANN, that is a multi-billion benchmark. We are using 1 billion of vector and a HNSW to execute the approximate nearest neighbor search with a recall of 96%. And you can see how with the optimized read feature enable, the yellow line, when you increase the concurrency of your clients up to 96 clients, can speed up more than 9 times the query per second execution. So it's a huge improvement. And in the next graph, we can see instead the comparison between 2 different generations of processors. We are comparing a Graviton 2 with a Graviton 3. The R6G, the orange one, is the Graviton 2 generation, and the R7G, the yellow one, is the Graviton 3. In this case, we are executing an approximate nearest neighbor search, increasing the EF underscore search parameter. Do you remember, if you increase this parameter, the recall increase, a more accurate result, but on the other end, you will consume much more resources, and the response time is higher. And for each test, the R7G is better, and you can see how at the extreme right with 800 for EF search, the improvement is more than 60%. So to summarize, the right choice of the hardware is also, it's also matter, no? It's important. And finally, an example of the integration between Aurora and Amazon Bedrock. In this case, we have configured the AWS underscore machine learning extension on an Aurora cluster, and you will be able to access the foundation models provided by Amazon Bedrock, invoking 2 APIs. The invoke underscore model underscore get embeddings and the invoke underscore model. In this case, we are using the AWS underscore bedrock dot invoke underscore model function to retrieve, to send a question to the Titan Text Express v1 foundation model in Bedrock. This is the input text, and we will get the response in a JSON format to your hardware. This integration is particularly useful in use cases as note summarization, product catalog search, and sentiment analysis. Okay, and as promised, if you want to dive deep in this topic and better understand the mechanism of similarity search, you can access the AWS blogs, but also the Jonathan Katz blogs. Jonathan Katz is one of the Amazon Aurora product manager in AWS, but is also one of the main contributors of the Postgres community, especially for the pgvector extension. So his blog is super up to date. You can delve into some very interesting concept as quantization. And finally, in AWS News, you can stay up to date with the last feature that we'll release periodically. Cool, that's all. Thank you so much. it has been a pleasure to be here today. Sofia is amazing. You are amazing. And if you need any help if you want to deep dive some specific topic, Tony, me, and our team, we are available. Here are our links, LinkedIn links. And before the Q&A, I kindly ask you to take 1 minute to access the survey. And yes, we are super interested in your feedback, and for us are very, very important. So thank you again.
Yeah, thank you, everyone.
Any question in the meanwhile? Please. The microphone. Sorry.
Hi, and thank you for the presentation.
My pleasure.
So we are building RAG architectures with Amazon Bedrock, and we have a use case where the customer will specify the subset of the documents that we need to query from the vector database. So imagine he asks for a product, the product has a version, and different versions of products have different technical documentation that we embed. So can you talk about a bit of metadata filtering? Because that's, I think, the thing that we have to do. And how can you configure metadata filtering in a Bedrock agent?
Metadata filtering.
Yeah, essentially linking the vectors to the source of the document so that, for example, if I ask for a product of version 5, I would only get the vectors from document that describes technical specification for version 5, because there are other documents that specify different versions, and I don't want the vectors from them.
And what vector data store are you using in your specific use case?
We are in the testing phase, and we're discussing between Postgres and Pinecone.
Okay.
No results already.
No, because, for example, for relational database as Postgres, you have also the capability to join your vectorial data with transactional data. So to filter the vector inside a specific table by a specific column. Also leveraging on transactional indexes, no? To reduce the scope of your knowledge base, let me say. But probably for each different vector data store, the mechanism is different. Anyway, we can follow up this specific use case and find the best solution to filter the data through Amazon Bedrock directly.
So how would you approach this with Postgres? Are you going to embed different technical documents into different tables, or use metadata for?
No, the same tables for all technical documents. But for example, for each document, you will have, I don't know, document type, document ID, different columns, yes. That's a column that specifies the version. And you can execute a query filter on the metadata related to the version. That is a column in a table. Because behind this column, there is the column with the embeddings. So here, the plus of using the same transactional data, transactional data store, is that you can collocate the vectors with the transactional data.
Yeah, okay, makes sense. Thank you.
If you do want some assistance with it, give us a shout as well, and we can link up after this as well.
Sure.
So yeah, keep working with you on it. Yeah.
Thanks a lot.
Or you can also join different tables, the tables with the embeddings and the tables with the version. Yeah, you have a lot of capability. Yeah.
Thank you.
Don't be shy. Eh?
I think everyone wants to go home, or
but
at
it's
least
late,
go and have
probably.
a beer.
We can catch up
yeah, please chat to us
with
out
a
there.
beer.
Yeah.
Yes, and okay.
Thanks a lot, everyone.
Thank you so much.
Thank you.